Welcome back to Codex. Our speaker today is Stefan Steinerberger, who's an associate professor at the University of Washington. Professor Steinerberger studies a wide variety of research problems using tools from PDEs, spectral theory, and harmonic analysis. Today, he'll talk to us about graphical designs. Take it away, Stefan.
All right, thanks so much for the introduction. It's a lot of fun to talk to this community about this stuff, because I think it's actually a lot of fun. And I'm trying to keep it fun throughout. So there's going to be a lot of pictures. There's not going to be too many equations. And feel free to interrupt me at any point. Okay, this is sort of supposed to be fun because it is fun. Okay, so I'll tell you the story sort of how I got this sort of canonical. It will, like, if I start with the definition, it won't make sense. But if I start sort of my thought process that took multiple years, it will all sort of come very naturally, and it will all make a lot of sense. So here's a vague question that I like a lot, because you can think about it for a really long time. If someone wants you to put endpoints on the sphere, how should you do it in the most regular way? Okay, and I'm very vague on what it means the most regular way, but suppose you want, for example, that, the average value of functions evaluated in these points is roughly the integral. What do you do? And this question is already very difficult on S2. And let's stay with S2. And there's a couple of sort of natural things, right? For example, if you want to put 4 points, probably you want to put them in the shape of a tetrahedron. But there's so many beautiful reasons why this is good that it's sort of hard to sort of condense anything out of it. Let's start with something very, very basic. If someone gives you 24 points to put on the one sphere, surely you should put them like this, right? Equispaced. And okay, you can rotate them, and that shouldn't make a difference, but that has to be sort of the best thing you do. If you come to me and you say, here's one way of defining the most regular set of points, I will test it on S1. And if this is not the answer for 24 points, I will say your concept is wrong. It's sort of a minimal requirement. And of course, there are many concepts that give you this. So that's not the problem. Next one. If you can put 12 points on S2, I want this to be a dodecahedron. And if it's 20 points on S2, I want it to be an icosahedron. And why? Because Platonic bodies are the best, right? And of course, the problem with Platonic bodies is they're so awesome that there's not too many. And if someone asks you to put 21 points on the sphere, or 13, right, then I have no idea. Right? I don't know. But 12 got to be a dodecahedron. 20 has to be an icosahedron. And there's one sort of amazing idea that I like a lot, which goes back to Sobolev and Lebedev. And this is Sobolev-Lebedev quadrature. And, if you look at the original paper from 1962, it's sort of very terse, you would say, right? It's like starts a lot with equations quite quickly. I would not, don't read this. The idea is very, very simple. The idea is very, very simple. It says, I want, how about I require that this is an equation for a suitable class of functions, right? That's what you could do, right? You'd say, oh, I want this to be true for constants. Okay, for constants, this is always going to be true. I want it to be true for linear functions. I want to, then the question is, what sort of function class do you pick? And what Sobolev proposes to take the spherical harmonics. So the spherical harmonics, such as harmonic polynomials on R2 or R3 restricted to S2, or there are also the eigenfunctions of the Laplace operator on the sphere. In a very canonical sense, they are the smoothest possible functions that are mutually orthogonal. So as you have more and more of them, they start oscillating more and more. They're really nice functions. And here's a couple of pictures what they look like, right? You have these standard, beautiful spherical harmonic pictures. And what Sobolev proposes is, how about we just put the point in such a way that this is true for constants? Okay, that's free. All linear functions, all quadratic polynomials, all spherical harmonics of degree 2, all spherical harmonics of degree 3, and so on, as long as we can. Because at some point, you're going to have too many equations. You're going to have too many conditions. If you put 25 points, you cannot hope to have this an equation for 5,000 polynomials. But sort of the idea. So let's go back to our minimal requirements and check it, right? If you take the harmonic polynomials on R2 and you do some math, you realize it's just a classic Fourier series. And of course, there's this sort of elementary fact that keeps popping up again and again, which is equispaced points integrate sines and cosines perfectly, meaning they give you 0 when you evaluate at equispaced points. up to a suitable frequency. At some point, of course, it starts failing. But the frequency is exactly the number of points, or one less. Maybe there should be n minus one, but okay. And then you can check it for this example, and it turns out this actually makes a lot of sense. So what happens here is if you put the 12 points on S2 in the form of a dodecahedron, then you can integrate all polynomials up to degree 5. And I want to really emphasize this because 5, the vector space of polynomials of degree 5 happens to be 36. So there's a 36-dimensional vector space on which this desired relation holds exactly. But we only have 12 points. So it's somehow solving 36 equations with only 12 points, which is really cool. And now you could say, well, wait a second, each point here has 2 coordinates, right? It's a 2-dimensional surface, so there's really 2 points here. So I have 24 variables if you want. Still, I'm solving more than I should. And the reason is that there's intrinsic symmetry in the vector space of polynomials. Okay, now here's the general question, right? Someone says, I want you to distribute n points on the 2-sphere. How many polynomials can I hope to integrate? And there's a sort of basic undergrad linear algebra heuristic, which says, each point has 2 coordinates, x and y, right? It's a 2-dimensional manifold, you have 2 parameters. So somehow if you have n points, you should have roughly 2n parameters. And 2n parameters should be able to solve 2n equations. So you should be able to go all the way up in the vector space until you have 2n equations, and those you should be able to comfortably solve. And more than that, as in the case of the dodecahedron, you should maybe not expect to be able to do it. And if you allow for weights, then each point has now 3 parameters, right? 2 coordinates and 1 weight. So you should be able to solve 3n equations. This is a completely open problem. Like this is far from resolved. There's even very little progress, I would say, in the last 20 years in this direction. And numerically, it makes a lot of sense. So this is a beautiful paper by Arens and Belkin. And this is an example of 302 weighted points on S2. And they integrate all polynomials up to degree 29. And this is a vector space of 900 polynomials. So we have 900 equations. And we have 906 parameters. So we should be able to solve it. And in fact, it can be solved. And here's a solution. And you see there's sort of, the 3n heuristic is very accurate, it seems. And there are papers about how to find these points, how to find these weights. And this is sort of a wide open problem in some sense. Okay. Then I'm going to start with sort of the seminal result in this direction, which is Delsarte, Gödel, Seidel from 1977. And they call, they formalize the definition. And this is a set of points is a spherical T design if this relationship holds for all polynomials up to degree T. And you can write down that, do some binomial coefficient math, and you realize the dimension of this vector space is roughly T to the D. And there's some constants you could compute. Okay, so the question is, what's the relationship between the dimension of the vector space and the number of points? And what they prove is what I call a No-Miracles Theorem. So the thing that we saw for dodecahedra, or maybe icosahedra as well, can't really happen when there's a lot of points. So it turns out if you have a spherical design, right, if you have a set of points that integrate, okay, this is, I guess, sort of tautological. Well, if you go all the way up to degree T, it's a vector space of roughly T to the D points, and you need up to constants as many points as the dimension of the vector space. There's no miracle where, hey, there's an amazing arrangement of 5 million points on S2 such that suddenly you integrate the first 10 to the 100 polynomials. This does not happen. You need roughly as many points as you want to solve equations, and comparable to the size of the vector space. And this, the implicit constant here is unknown. The natural heuristic is exactly the counting I told you. If you're in D dimensions and you have unweighted points, you have D times N coordinates, and then you compute the constant here, and that should be exactly it. And even any deviation at the scale of constants would be a miracle, and we don't expect that. Okay, and there's a lot of people who worked on this, and I don't want to omit stuff. So at some point I went down and I went through all the papers I could find, and I almost missed a flight. I did this at the airport. And there were so many papers, and at the end I had to run. I sort of missed the fact that Reporting. Okay. Lots of work. I cannot possibly or explain it all, but it is a very interesting problem, and there's been a lot of stuff that's been done. Okay, and so the question is this sharp? And the answer is yes. And there's sort of a result from maybe 10 years ago that shows that you can always do the scaling as well. Again, there's a constant that's sort of missing. And this has been refined by various other people after that. But it turns out linear algebra is roughly correct. And if you want to do this, then, you know, the vector space is roughly comparable to the number of points. Any questions up to now? We're good? Okay, so this is sort of fun. But then I thought to myself, well, you could ask the same question on the torus, right? Because, you know, what's changing? Well, what's changing is you can't really use polynomials here anymore, right? Because polynomials make sense on the sphere because the restrictions of polynomials in space. But, you know, polynomials don't make sense on the torus. But I know functions on the torus that are meaningful and low frequency and orthogonal. You just replace the polynomials by trigonometric polynomials. In some sense, this is almost easier, right? It's easier to write down. And there's a natural ordering on, you know, how high frequency a trigonometric function of this type is, because, you know, the frequency is right here, right? So there's a natural ordering how they come about. And I could ask myself the very, very same question. I could say, hey, I want to find endpoints on the true torus in the most regular manner, and most regular being defined in such a way that this is true for as many points, for as many functions as possible. So given n points, I want this to be true for as many trigonometric functions as I can. The same question arises, what can you do? What can you hope for? And the question is also like, you know, maybe there are miracles now, right? Maybe there are interesting constructions. And it turns out you can just take a grid. You take an n by n grid. And when you now write down the Fourier coefficients, you realize they sort of decouple because x and y are independent. And then you're back to the standard one-dimensional equispaced computation that we've done already. And you have it twice. And you realize this thing's actually, you know, this one satisfies, you know, it's you know, both sides are zero. But if you plug a trigonometric function in, this is zero. And this is also zero for the roughly first n frequencies. And it turns out there's a result by Hugh Montgomery from the 1980s, which is sort of the analog of the No-Miracles Theorem, which says, you know, you can't really hope for more than this. So n points, you can hope for n to solve n equations. You will not solve n squared equations with n points. There is no miraculous construction of points that does this. And this was actually done in sort of a very interesting sort of context that's more closely related to irregularities of distributions and combinatorics. So I'm not going into that, but it's a very, very beautiful Fourier analysis trick. Very nice paper. Okay, so now you could generalize even more, right? And you could ask yourself, okay, what do these two examples have in common? Well, what are the spherical harmonics on the sphere and the trigonometric functions on, I shouldn't call them exponential functions, the trigonometric functions on the torus, what do they have in common? Well, they're both eigenfunctions of the Laplacian on the manifold, right? Which one could really argue that eigenfunctions of the Laplacian are sort of the canonical low-frequency basis on any given manifold. Now, if you don't feel like you have a good idea what this means, welcome. This stuff's sort of difficult. I've been trying to understand it myself for a very long time, and every year I keep trying. But in any case, okay, so you could say this is sort of the natural generalization. You could ask yourself what happens on general manifolds, and it turns out there is sort of a beautiful general theorem, a general no-miracle theorem, that says no matter what you do on any compact d-dimensional manifold, if you have n points and you want them to integrate out the first n Laplacian eigenfunctions, or however many you can only hope to get a constant, not more than this. So this is a general sort of no-miracles theorem that works on all compact manifolds in all dimensions. And it says if n is large, there are no miracles anymore. You might have, by having extraordinary amounts of symmetry, it is conceivable that you have something like the analog of a Platonic body that has a lot more symmetries than you'd expect, and somehow it integrates more points than you think. But that's sort of only at the very beginning for few points. The moment n gets large, there's nothing you can do. And in fact, the proof actually gives a constant, and the constant is sort of terrible. I think that's growing still exponentially, at least, so it's pretty bad. I think the optimal constant has to be d if you do unweighted points, and it's going to be d plus 1 if you do weighted points. This result actually covers weighted points as well. So even if you put little weights, you still cannot hope to do more than a linear number. Cool. Any questions so far? Okay, so this is sort of the, if you want, the abstract, this is the pathway, right? You start with spherical designs. These are very classical objects. They're very beautiful. They're very hard to find. The constants are unknown, but somehow linear algebra tells you what's happening. Linear algebra does not tell you how to actually find these points. And it's a really interesting problem how to like find good points. It's not so easy at all. If you allow weights, it seems to get a little easier, but it's still very difficult. And then you realize you can do this on sort of all manifolds, and it's probably not going to get easier if you move away from the sphere. Okay, and now let's go discrete. Okay, so for the rest of the talk, this is sort of now I think it all makes sense, what I'll say next. Let's move to the discrete setting. So at some point, so this is George Lindemann, who was a former graduate student of mine, who's now a doctor, medical doctor. This is actually MD, PhD. It's pretty rare. And I always used to talk to him about like various things that I did that I thought were very pure and useless because he worked on very concrete applied things. And I once told him, hey, this is like really useless what I just did, imagine. And I explained it to him and he said, oh, this actually is useful. And here's what he explained to me. So George was working on a blood pressure problem. So what he had, I'll just tell you the story. It's very interesting. They had health data for like 1 million people. And the question was, what's the average blood pressure in this population? And the blood pressure was not part of the data they had. So a natural sort of ansatz you could make is, okay, I got 1 million people. I'm going to turn them into a graph. I'm going to connect 2 people if they are very, very similar in terms of the data that I do have. So nearby points will be connected in a graph. And then I'm just going to pick a couple of points in the graph, and I'm going to go there and measure these people's blood pressure, which is what they actually did. So you can realize if you like actually have to measure like the blood pressure of 1,000 people, that's logistically non-trivial. So you want to get sort of, you want to get very good results incorporating the information you already have. So here's sort of the basic problem, which I think is completely understudied. I think this is a really fascinating problem. Someone gives you a finite graph, and suppose it's unweighted and just basic combinatorial, that's already difficult. And you have an unknown function from the vertices to the rails, for example, blood pressure. And you want to now find the average value of this function over the graph, meaning you want to integrate the function, right? But you can only evaluate the function in 3 vertices. Assuming that the function is somehow connected to the geometry of the graph, meaning sort of, the easiest case would be it varies very slowly across edges. What are the 3 vertices that you want to choose? And replace 3 by any parameters you like. And George actually had to deal with this. They had a graph, and they realized if you put 100 people at random, you have standard sort of Monte Carlo heuristics, and it's not going to be that bad. But the question is, can you use the graph information in sort of an additional ingredient? And what do you get? So here's an example that we did. This is an actual graph. And George and I proposed some algorithm, and this is what the algorithm tells you. If you're allowed to sample 3 points in this graph, these are the 3 vertices and the weights that you're allowed to sample in. I'm not going to go into the method. You can think this is absolutely terrible, right? Until you know 3 better points, and maybe you're right. Completely, here's the reference. Everything here is open. I think this is a really fun problem that's completely unexplored because it's not even quite clear how to make it precise. There are many different ways, and we have one. And it seems sort of reasonable, right? So we ran it on MNIST, we built an MNIST graph, we tried to sample the number of 5s and the number of 7s, and it sort of worked. But I think this is a fantastic problem. Okay, I'm going to be very precise on this. And now I'm going to give you vague philosophy that will lead us to graphical designs. So what's the vague philosophy? This Sobolev-Lebedev ansatz of how to find points gave us beautiful points in Euclidean space. It gave us Platonic bodies, right? And the analog of Platonic bodies if the number of points does not happen to be one of those 5. So we could try to carry everything over. We could try to do everything on a graph and see what happens. And the question is, how do you carry it over? And then there's sort of the beautiful question is, what's the analog of a Platonic body on a graph? What's the most beautiful sort of subset? That was sort of the original vague philosophical motivation. I'm very vague here. Any questions? Any comments? Okay, so we'll take a finite simple connected graph, everything nice, everything friendly, everything unweighted. You could weight things, everything unweighted. And we've got a nice sort of way of integrating functions, just, the average value. And now the question is, what's the analog of a polynomial or a trigonometric polynomial, or this was already sort of combining both, a Laplacian eigenfunction? Well, lucky for us, there is a Laplacian on a graph, right? Because you think a Laplacian is really just sort of measuring local averages. So if you've got a function on the vertices that give you a real number, then the graph Laplacian is just another function on the vertices, the Laplacian of the original function. And how do you define it? You define it as sort of, this is one way of defining it as the, you take a fixed point, you look at all the neighbors, and then you see whether the function average is sort of how it compares to the local average. So this is one possible Laplacian. There are at least 3 or 4 natural Laplacians. Luckily, they all agree if the graph is regular, if every vertex is the same degree, and all subsequent examples in theory I will present are for regular graphs. So we don't have to worry about which Laplacian do you pick and how does this all depend on the Laplacian. Okay, everything's going to be sort of nice and canonical. And of course, Laplacian, what it does, it sends functions to functions. It's a linear operator. And functions are just in sort of n-dimensional vector space, where n is the number of vertices. So the Laplacian is simply an n-by-n matrix. And an n-by-n symmetric matrix with eigenvalues and eigenvectors. Okay, symmetric already requires some Laplacian, but okay, we're good, we're good. So we got eigenvectors, we got eigenvalues, and so you could now think of these eigenvectors as the natural analog of polynomials, trigonometric polynomials, Laplacian eigenfunctions. So now I'm going to give you a definition. I will say that the subset of a subset of vertices of a graph is a graphical design. If it integrates, it's the same definition as Sobolev-Lebedev, if for as many eigenfunctions as possible, here eigenfunctions are really eigenvectors, of the graph Laplacian, the local average in the set of vertices equals the global average. And for almost all natural cases that we're interested in on regular graphs, these eigenvectors are orthogonal, and the first one is constant. So this right-hand side is usually just 0. So you could even think of this as actually being 0. So what we want is, given a certain graph, we want to find a small subset, right, the smallest possible, such that for as many eigenvectors as possible, this is satisfied. And one natural way of thinking about this is, hey, if I take my function on the graph and I expand it and I write it as a linear combination of the eigenvectors, and I then sample in this set of points, then this relationship just tells me that I don't make any errors on the subspaces where this is true. I'll make errors in a complement, and that's sort of unavoidable, but that's life, right? That's sampling. You're always going to make errors somewhere. So the question is, well, do they even exist? Should they even exist? What's going on? So I had this definition and I started looking at examples. And I'll just show you some nice graphs. What you see is your graphs, and every vertex that's circled, that's something in the graphical design. It turns out this is a graphical design of size 8. And out of the 32 eigenfunctions, it's got 32 vertices, so 32 eigenfunctions, 16 are integrated exactly. And you see they're sort of nicely spread throughout the graph. And if you look sort of carefully, you can actually see something funny, which took me weeks to realize. Each vertex is either in the design or it's distance 1 from exactly one element in the design. Like if you take this one, it's one neighborhood to this one. And if you take this one, it's one neighborhood to this one. And this one's adjacent to this one and no one else, right? It's sort of very funny. And they tend to do stuff like this. So this is the Nauru graph. And here 6 vertices integrate 19 out of 24 exactly. Linear algebra tells me with 6 vertices, the six variables, the best I can hope for is satisfying 6 equations. Here I satisfy 19. which means these are really excellent sampling points for this graph. Here, McG graph, 8 to 21 out of 24. The generalized Petersen graph, 8 vertices integrate 22 out of the first 24 eigenfunctions. So there's some very interesting magic going on. And my argument is these are actually the analogs of Platonic bodies. So if your universe is now the graph, this subset is sort of the analog of a finite cardinality set with exceptional symmetries. And the symmetries are reflected in the fact that, you go way above 8, you get 22 out of 8. 22 minus 8 is what, 14. That's like 14 degrees of symmetry that are being captured somehow. Okay. Sylvester graph, 6 vertices integrate 26 out of 36. And I could keep doing this, right? So there are many, many, many examples empirically. So here's the first result. I proved that these things are decidedly non-Euclidean in the following sense. If someone gives you, if you have a subset, then there's a couple of cases that can happen. Maybe it's terrible. Terrible means, okay, it doesn't actually satisfy all that many equations. Maybe you have a subset of 20 vertices and satisfies 15 equations. Yeah, that's not very good. Okay, sure. And that you can always do. You can always build terrible examples. Or maybe the set is huge. So it could be that, for example, you take all the vertices, then of course many equations are satisfied, but we don't really care about that because it's not really sampling if you look at everything, right? That's the whole point, is to have W small. Or if you have a small set that is also good in the sense of integrating many equations, like the ones that I've shown you here, they're pretty small. Then, what happens is you have an exponential growth of neighborhoods. So what happens is if you look at these sets and you look at how many vertices at distance 1, how many vertices at distance 2, how many vertices at distance 3, then this has to grow exponentially until it hits the entire graph, until you have everything. So you realize that these structures are intrinsically non-Euclidean because the volume growth in n dimensions is like r to the n. It's polynomial. It's quickly polynomial, but not exponentially. Here it's exponential. So these things are profoundly non-Euclidean. And that's why I think there are many more of those than there are Platonic bodies. And this was actually funny because I proved this theorem and then I went back to look at examples. And that's when I realized that, in fact, all the examples I had, everybody is connected to exactly 1. So each vertex is either in this design already, or it's exactly distance 1 from exactly 1 element in the design. So the 1 neighborhood is already the entire graph.
So Stefan?
Yeah.
Is like the Hamming code.
Oh, Dustin, give me 2 slides.
Okay, cool.
Great question. Great question. Yes, codex, right? So yes, absolutely. Okay, so it turns out the examples I had, actually the 1 neighborhood is always the entire graph. Turns out, like, you look at this one, right? It's adjacent to that one. You look at this one, adjacent to this. Right, so the theorem is actually sort of true, right? It's always true. It's a theorem, but okay. And then I give some talks on this, and after that you give talks, and then someone says, "Can you send me your slides?" Right? And you send the slides, and you never hear from the person ever again. But there are wonderful counterexamples that happen, too infrequently, and this is one. So Konstantin, he asked me for slides. And his motivation was the following. So there are a couple of very sparse, interesting examples that have a small set here, that's a set of 4 vertices that integrate 11 out of 12 eigenfunctions exactly, all but 1, which is absolutely miraculous. Of course, you cannot integrate all of them, right? Because you could always, by definition, if you sample, you lose information. You get to lose some information. Otherwise, you can't reconstruct. You could take a function that's 1 here and 0 everywhere else. That can't satisfy the equation if it's a subset. So this is the most extreme you can do. There's some few examples that do this. And Konstantin calls this an extremal graphical design. It's a set that integrates all but 1 eigenvector exactly. It's the best we could possibly hope for. It's the very, very best. And above you see 1. And he had an amazing insight, which is the following. So it turns out if you have a graph, there's a combinatorial quantity called the independence number, which is the largest vertices that you can pick, the largest number of vertices, such that no 2 of them see each other, no 2 of them are connected by an edge. So that's it's like a packing problem, right? And there's a very classical bound in combinatorics called the Hoffman bound, which says if you have the spectrum of the graph Laplacian, you have the eigenvalues, then you can give a spectral bound on this quantity. And the spectral bound is this. And sometimes it's sharp. And what Konstantin proved is says if the Hoffman bound is sharp, then this independent set is actually an extremal graphical design. So this suddenly connects a couple of different fields. It's very, very fun. And I'll give you some spectacular combinatorial examples. So this is the Erdos-Ko-Rado Theorem. And this actually is a funny story. Apparently it was written in 1938, but back then no one cared about combinatorics. It was only published like 20 years later. And now it's one of these foundational results in extremal combinatorics. And the statement's very nice. So suppose you have a collection of k-element subsets of 1 to n, such that any two elements in your collection have an intersection. They have one element in common. Now, it's very, very clear that A cannot be too large, right? Because if you had all n choose k subsets, then you can pick some that don't have any elements in common. So the question is, how large can A be? And what they prove is they prove this wonderful bound. And the example is just take all the subsets that contain the element 1. Then, of course, any two sets in your set A have a common element, which is 1 by design. And it turns out this is the best you can do, right? And then, you have n minus 1 elements to choose from, and you have to choose k minus 1 from them because one you already took, which is A, 1. And that's how it goes. So it's a very, very beautiful result. And there's now many proofs of this. And it's really one of these foundation ingredients. So it turns out you can do a graph theory version of this. So you could look at the graph that's given by all k-element subsets. And you connect any two subsets, which are now vertices, if they are disjoint. So this is what's happening here, right? I mean, this is the 5-element sets, and you see these two all disjoint. And this is known as the Kneser graph. Okay, so that's nice. And it turns out what you're looking for is now you're looking for the largest number of things, of vertices that are not connected. Because if they're connected, they have an empty intersection. You have no element in common. I want all of them to have an element in common, so I want them to be unconnected here. So I'm looking for a large independence number. And it turns out extremal configurations in this are all extremal graphical designs on this graph. So now you have a large sort of infinite family of extremal graphical designs. It turns out the very same result holds for the Deza-Frankl theorem, which I won't talk about. It's about fixed points of permutations. A similar kind of story. You're looking for the independence number of a graph. The Hoffman bound is sharp. Everything's an extremal graphical design. So I thought this was really fun. Very, very nice. Okay. Any questions on this? Okay, we're good. So then it turns out that there's been lots of recent, very exciting work by Catherine Babecki and Rekha Thomas, and I'll talk about that. So they started proving a really, really fascinating equivalence theorem, where they showed that you can construct something that's known as an eigenpolytope of a graph, and I'm not very qualified to speak on this, but it associates to each sort of graph and the corresponding eigenvectors a polytope in high-dimensional space, and it turns out there's a one-to-one equivalence between graphical designs with positive weight and the generalized eigenpolytope. I cannot, there's probably people in the audience who are infinitely more qualified than me to speak on this, and I'm barely qualified, so I won't. But I'll tell you about one sort of fundamental. This is a picture from their paper. Sort of gives you a flavor of these things sort of look like. It turns out there is one immediate consequence that is absolutely gorgeous, which is that graphical designs exist. What do I mean by this? I mean that if someone gives you a graph and someone gives you a number k, you can always find a set of k vertices, say 5 vertices, and associated positive weights on these 5 vertices, such that this set is at least a graphical design for the first 5 eigenvectors. So the linear algebra heuristic is exactly correct, in a sense that you can always hope, you can always construct examples that do this. So if you think back to linear algebra, right, we have these equations that we want to satisfy. There's a basic linear algebra argument that says with underdetermined system that if you give me any 5 vertices, I can always find 5 weights. such that any 5 equations are satisfied. This is just because under determined systems and stuff. The crucial ingredient in this theorem is that the weights are non-negative. The weights are actually positive, which is what you want in sampling for numerical stability and just overall beauty of the construction. Like the entire theory here is always non-negative weights. And linear algebra, sort of undergraduate linear algebra, only gives you the existence of weights, not that they're non-negative, and now this general equivalence theorem gives you that they're in fact non-negative. Now here's where the gap lies, right? 5, 5, someone gives you the number 5, you can find 5 vertices with weights such that this is true, but sometimes they're much better, right? Sometimes they get many more eigenfunctions, as in this fruct graph example we've just seen, where 4 give you 11 out of 12. So this is sort of where the fun is. Okay, I'll give you now let's go to expander graphs. It's sort of the next sort of natural connection. So if I have a graph, I can do a random walk, right? And what does the random walk look like? Well, the random walk says I start in a vertex and I go to a random neighbor. So among all my neighbors, I pick one uniformly at random and I walk around on the graph like that. So you could write this down very nicely. You start with some initial vector mu0 that gives you your probability distribution of where you start. In particular, you could just have entry 1 somewhere and entry 0 everywhere else. That would correspond to starting in a deterministic vertex. And then the process of taking a random neighbor and going there just corresponds to multiplying with this matrix, where A is the adjacency matrix and D is the degree matrix, which is a diagonal matrix collecting the degrees. And it turns out that's just a fancy linear algebra way of writing the random walk. So the random walk is just given by this. So it's just taking large powers of a matrix, which is great because we know everything, right? But large powers of a matrix. And there's sort of a basic fact from, if you want, well, it's not even Perron-Frobenius, it's just spectral theorem somehow. Well, what happens is this thing has one eigenvalue 1, and that corresponds to the stationary distribution. And then all other eigenvalues are less than 1. And which means that if you keep doing this, it's like a power method. You converge to the largest eigenvector, which is the stationary distribution, and the rate at which you converge depends on the second largest eigenvalue. And so the game is now on, right? So you could now, for example, take something like a complete graph. In a complete graph, you have excellent mixing properties because within 5 steps, you could be anywhere, right? I mean, within 1 step, you could be anywhere. And so the expander graphs are now sort of restricting the game a little bit and saying, okay, you want lambda 2 to be really, really, really tiny, meaning you want to have excellent mixing properties. You want that the random walk immediately goes to the stationary distribution at the fastest possible rate. But you also want to have very few edges, because if you have a lot of edges, a lot of like interconnectedness of the graph, then this is sort of easy to do. And the picture is always you have like n computer systems, and you want to be able to send information from any computer to any other computer as quickly as possible, having as few lines, physically cables that you have to put down. Okay, so I'm not going to talk about expander graphs, but this is sort of a general setup. And now here's the second fact from linear algebra. If you start with some sort of generic initial measure, anything here, right? Generically, what's going to happen is that this is exactly the story, right? You're going to converge to the uniform distribution at the rate given exactly by lambda 2. Because if you expand your initial vector in terms of the eigenvectors of this matrix, for a generic vector, you are not orthogonal onto the second eigenvector. So if you do the power method, that one's going to dominate asymptotically. So this is sort of the story. And this is why everyone in the expander community cares about lambda 2, because it tells you the full picture. It tells you the generic picture. This is what's going to happen. So here's a fun picture. By the reasoning that I've just told you, most probability measures on this graph, almost anything you pick, converges to the uniform distribution at a rate that's given by second eigenvalue, which is 0.78. So after n steps, you expect that the difference between your actual probability and the uniform probability is 0.78 to the n, and there's some constant at front, which I'm not tracking. So the constant is not small, but you have exponential rate to a uniform distribution. But it turns out if you start with the uniform probability measure on the 4 red vertices, which I've highlighted, then the random walk converges much, much faster. And in fact, it converges at a rate given by 0.47 to the nth power. So not faster at the level of constants, exponentially faster. And of course, this cannot generically be true by basically an algebra spectral theory. But there are these exceptional initial distributions that converge faster. So in terms of like computer networks, I would think that these are great locations to put a server, right? Because this sort of the random walk spread much nicer. Okay, so what Rick and I did recently, as sort of as a follow-up of their result, is we proved that this is sort of generally possible. So if someone gives you a connected regular graph on n vertices, then you can pick any number you want, say 4, and then there exists a probability measure supported on some set of 4 vertices. And it's a probability measure, so non-negative weights, but not necessarily equal weights, not necessarily uniform. Such that the sequence of measures that you get from this random walk converges faster than lambda 2. And in fact, the convergence rate is, here it's a 2k because I'm taking an L2 norm. So after k steps, it's if I take a square root, it's the kth power, it's an exponential rate. But the index is the eigenvalue lambda L plus 1. These are sort of decreasingly ordered. So what happens is, lambda 2 is the largest, lambda 3 is the second largest, lambda 4 is the, and so on. So what happens is, generically converge with lambda 2. But there are subsets supported on 4 vertices, such that, so subsets of 4 vertices with probability measures on it, such that the random walk converges much, much faster. And much faster here means at the speed of lambda 5, not lambda 2. Which makes you revisit the entire sort of expander idea, right? Because expander graphs, the entire theory, which is very beautiful, very deep, very rich, right, is concerned with minimizing lambda 2. But now sort of the game's different, right? Because I could also ask about lambda 5. Minimizing lambda 5 suddenly makes sense. Because while lambda 2 is the generic rate, I know there are exceptional sets that start on 4 vertices, only 4 vertices, that achieve the lambda 5 rate. So you could ask, how small is that? How do you construct examples? Any questions on this? Okay, so I think it's 50 minutes, right? Roughly. Okay, cool. So Dustin, hypercube. There's a beautiful paper on exactly this, showing that the Hamming code in the cube graph is actually an exceptional graphical design. It's really, really good. And in fact, it's the smallest possible linear code that integrates a certain number of eigenfunctions if you want them to. And Catherine has a conjecture that the Hamming code is in fact optimal. So yes, all of this also naturally interacts with coding theory. And Catherine is infinitely more qualified than me to speak on this, and she has a very nice paper on exactly this subject. Okay, and I'll finish with some bad news, right? So far, I've been telling you this is all nice and beautiful and pretty. It turns out there is the general linear algebra bound, and you're guaranteed to find sets of that size. Whether you can find better sets is NP hard. And in fact, counting the number of minimal designs is also P complete or star P complete. Again, I'm not too qualified to speak on this, but so it turns out it's sort of a very, very difficult problem to do this. Catherine has a collection of very nice examples of graphical designs on this webpage. And one way that they're being found is often sort of linear semi-definite programming, where you're looking for sparse vectors, such that when you multiply them with a suitable matrix, you get, basically what you find is you're given a matrix, which are the entries of the eigenvectors. And what you want to find is sparse vectors in the null space, which is sort of a hard problem, but you can do some semi-definite linear programming ansatz. You can put some penalty functions, and oftentimes you find these very beautiful examples. Okay, and with this, I finish almost on time. Thank you very much.
All right, let's thank the speaker by smashing one of these reaction buttons, and I'll stop the recording here.